phase diagrams, we have to talk a little bit about solubility first. And it's quite intuitive that the entropy of mixing is positive, because when you have two different substances, there's a lot of more ways to arrange those than if there were just one substance. And we see this from this equation. The entropy of mixing equals minus nr ln x. And so x is just the amount of substance that we have. It's a mole fraction, and it goes from 0 to 1, so it's kind of a percentage divided by 100. And so when this x is 1, when we just have 100% of one substance, the logarithm of 1 is 0. So there's no difference in the mixing entropy. But we see that when x decreases, the logarithm of a number between 0 and 1 is negative. So then this whole term turns positive. And when the entropy is positive, that's favorable for the formation or for a process to happen. And so why is it then that two substances does not always mix? Because mixing is an entropic, very favorable process. Well, we do have this formula for the Gibbs energy, where we also have the enthalpy here. And so we see that the higher the temperature, the more does this favorable entropy we get when we mix two substances. It plays a bigger role, because when this term is negative, the Gibbs energy is negative, and that's what we want. That's what makes the substance or process stable and favorable. And so we see here its temperature on this graph. We're going to go deeper into this picture later, but when the temperature is raised, we go from these two phases where we doesn't really have any solubility to the one phase region where we have full solubility of these two substances. So when we increase the temperature, and when we're at this point, for example, we have full solubility of the substances, no matter how much of these substances we start out with, because this is down on this line, it's the same as here, and it's the same as this x is the composition. And so now we understand that the enthalpy also has something to say here. And so we're going to try to understand this graph of the Gibbs energy of mixing of two different substances. And if we were to just graph the entropy of mixing, we would just get, obviously it would be reversed, but we would just get this single graph here, where we see that the entropy, or the Gibbs energy actually, it's most stable when we have 0.5% or 0.5 of both substances. But we do know that is, for a lot of substances, that is not the case. I'm thinking oil and water, for example. The more oil you put into the water, the less, or you will start to see that a phase of oil separates out from the water, right? So if it was just the temperature, the entropy that we were picturing, the graph would always look like this, the Gibbs energy graph. And so this factor here, it depends on H, the enthalpy. And we could think of it as when this factor gets higher, we have more repulsive forces against the two substances we are mixing, and so there will be a lot more energetically favorable for them to separate into two phases. because the attractions that they have to molecules, the same molecules, is more favorable than the attractions they have to another substance. So you see here when the number 1, then it doesn't really matter because the the forces between A and B is the same than the forces that they have in a phase with just one of these substances. And so when we start to get more and more repulsive forces between these two substances here, we will see that we're starting to get this graph. And so what we see is if we're up here and we have quite repulsive forces between the two substances, we will start up here. I'm just picturing two molecules right now, and then it would be a lot more energetically favorable for them to separate. Some of the molecules go down here and some of the molecules go down here, and then we will just have a lot lower energy. And so this is the phase separation. That's what's happening here. And we see that we have 0.5 of each substance here. Now what happened? Because here we can see that at this point we're having a lot less of one of the substances but a lot more of one of the other. And the same is here. But a very important point here is that the overall composition does not change. We're not removing or adding any substance, so it will stay the same. But it is just that these two different phases separate, and the composition in those phases are different. And so let's look at this picture and imagine that we would want to make a very simple phase diagram of two substances. For example, oil and water. And so what we would do is that, it's obviously the mole fraction of B down here to the right, because you can see that the substance B, we have more and more of it as we go to the right. And so we start with a lot of one of the substances, a lot of water, for example, and we add a little bit of oil. And then we see, it's soluble all the ways. And then we take away some water and we add some more oil. So we change the composition. The composition goes from here, where let's just say, the mole fraction of B is 1 here and 0 here. So let's say it's like around 5% or something. 5% of B here, and the rest is A. And then we subtract some A, so we have around, let's say, 75% A here, and 25% B. And so this is kind of a special point because we have an equilibrium between two phases, between the one phase region here and the two phase regions here. So we will see that exactly at this point, one phase will start to separate out. Here we have just two phases. We can't distinguish them from each other. It's homogeneous. And so when we increase the composition of oil here to around, let's say, 40% oil, 60% water, we see two phases. So we know that we're in the two-phase region here. And if we increase the composition of oil even more, we're still in the two-phase region, and then we come to this point here where we're at an equilibrium where the A phase is starting to disappear. So if we increase the composition just a little bit more here, then we will have full solubility again. And what we could do then is that if we heat up these mixtures, we could find the point at as where this mixture, for example, gets soluble, and then we have this point on the phase diagram. And we heat up this mixture, find out it's fully soluble here, and so we have another point at our diagrams. And now at least we have these 4 points. So we could then map out this diagram here, right? We would obviously need a lot more points if it was going to be accurate, but this is good for our purpose. And so the takeaway from this is going to be that at this temperature here, because we're at the same temperature all the time, okay? At one temperature, we have a specific solubility. The solubility doesn't change, right? And the solubility, as we see here, is around 25% oil in water, or 25% water in oil. And that is the general principle, that you will never have one completely pure phase, because the entropy of mixing, it increases so much when you just have a few more molecules of another substance. You will have so many more ways to arrange the system, that the entropy of mixing is huge just by adding a little bit. So there will always be a little bit of solubility in all substances, right? And this solubility at this temperature is marked here and here. And wherever we go at this diagram, even though we increase or change the composition, the solubility will be the same, because we're still at this specific temperature. So nothing has really changed except the composition. And so if I'm at this point, for example, where I have around 50% of each of the substances, I will go to the left and have this composition here in the water phase, and this composition here in the oil phase. So wherever I start here, at wherever composition I start, the two phases will always separate into equal compositions when we're at the same temperature. And so this is interesting, and is a very important takeaway. But what obviously does change, as we see here, is the relative amounts of the phases. There's a lot more of phase B here, and just a little bit of phase A here. But at this point, there's 50% of each of the phases. Right? So the composition in the separate phases is the same at wherever temperature we're at. But the relative amounts, that's what changes. And so when we move up here, when we're at another temperature, we see that the solubility here is different. It has increased. We can now have around, let's say, around 30% of B in A and 30% of A in B here, until we get to this point, right? Where we just have one phase at whatever composition we have, there's just one phase. So we're going to use this sooner on the binary phase diagrams.